is now a full interdisciplinary endeavor to really understand the physical behavior, quantum physical behavior of these molecules. What I believe is happening is that we are facing, at this time, what people would understand as a paradigm shift in the understanding of our molecules that support life on Earth. And this paradigm shift is going to change the way we can manipulate life processes at that molecular level. So we are starting to find a very different way to understand the quantum science that we can find in those biomolecular systems. And therefore, that opened the door for using many new tools from quantum science to affect those biosystems. And eventually, when these communities interact more often, and the communication and the understanding from the different perspectives becomes more cohesive, then we will be able to say a little bit more about the biology of that quantum regime. Now, as a theoretical physics, my aim is to build theoretical and computational approaches that will allow me to help accelerate that paradigm shift. That is my aim. And to do that, the core of what I do is centered on an idea that we call theory of open quantum systems. What this means is, who has the molecule? One molecule. There. So if you see that molecule, the molecule will have the yellow background, which represents the proteins, and it will have some structures that represents the chlorophyll. So if I move in this direction for a moment, whoever has the green molecule, this is a 3D version of the one that I'm presenting here in 2D. And in this molecule, these curvy structures represent a protein, and these black structures represent the pigments, which absorb the light individually when they are far apart, but collectively if they are interacting via their location here in this protein. These chlorophylls, or these different pigments, in this case, these are not chlorophylls, these are phycoerythrin, so it's another kind of pigment that will absorb light. They, from a chemical perspective, they are made of many different molecules, many different atoms, and they have a multitude of electronic states that you can investigate. From the perspective of open quantum systems, which is the perspective that I work, I see those systems, those electronic systems, as different electronic states, different electronic possible motions, quantized motions, as I'll explain in a moment. And everything is around the nuclei motions that come from the internal part of the pigments, the nuclei motions that come from the protein. I see that as an environment. And the reason we do this is because in the lab, we normally don't have access to all the possible motions that describe this system. So we have optics, which means that we are addressing the electronic motions in these molecules. So these open quantum systems allowed me to reduce a little bit the complexity of understanding the physics of this system, while at the same time, being able to build an explanation of what we are observing in the lab. Again, I try to, and when I say I, it's I and the research group that I lead. We try to integrate different methodologies from all these different disciplines to build a cohesive theoretical framework to understand this quantum behavior, to predict that what you might observe in particular experiments, and to be able to advance this understanding. Now, let's go to the meat of the problem. The main question that we're trying to address in this field is whether these systems support quantum processes. What do I mean by that? Let's go back to our molecule. So what is happening here is that this molecule is absorbing light, which I represent here with this wave. We know that this light is quantized, so the light is coming in packages that we call photons, and this system is absorbing these packages of photons. How is it absorbing this? Is already a quantum mechanical process that we all agree. When this light is absorbed, what is being affected by the absorption of this photon is the electronic motions of these chromophores or pigments. I will use different names as they are known in the literature. Now, what is the change of these electronic motions as these photons are absorbed? That is what is explained by quantum mechanics. Just to give you an insight, a picture of the quantum mechanical processes, I'm going to make an analogy with classics. Although we know quantum and classics do not necessarily have a direct correspondence. But the closest concept to understand what is happening with these chromophores is the interference that you see when you put two stones in a very calm lake. You put two stones in a calm lake, you form waves that propagate. And if these waves interfere, you will see some regions where you have black, some regions where you don't have. And what this represents is you have different motions of the matter here. Now, at the molecular level, before I go into that, the way we describe this is a superposition of the possible motions that come from the wave on the right and the possible motions that come from the wave of the left. At the quantum level, something similar can be used to describe what is happening there. But we don't have waves really there as what we have in the water. The waves that we have there is more about the probabilities of how we will affect the system and the motions that it will have. Now, I'm going to enter a little bit of the math, but don't worry, it's not a lot, but it will give you the main insight that then will allow us to understand what is happening in nature. If you imagine that now that molecule that is moving around is reduced to only two of those pigments bound to the protein. The different colors of these pigments means different light that they can individually absorb. And this on the left represents that if it hasn't absorbed, it's just in the ground state, and if it has absorbed this pigment, then it will be excited, and I'm going to call this 1. And on the right, it represents the green pigment. If it hasn't absorbed light, it's on the ground state, and if it has absorbed, it's on the excited state, and I'm going to call this the 1 of the left. It happens that when these pigments are interacting, the light that they absorb is neither red nor green. They absorb light at different frequencies. And for me to understand what is the light that they will absorb, I will use that concept of interference of the different states. From a more physical perspective, what is happening here is that there is a probability that when a photon is absorbed by this molecule, that this will be excited, but then because of interactions with the other pigment, it will get de-excited, but this one will get excited. Essentially, they are sharing the excitation, but the way they are sharing this excitation is similar to that interference pattern that we have. It's not just sharing by passing one another. I like tennis. I play tennis a lot. And if you want to imagine a little bit, if you play tennis, this sharing is as playing doubles. The ball is coming, and you are working in a unity if you play tennis properly. You are working in a unity to respond to that ball that you can imagine is the ball. This is a way of imagining this process. The main idea that I want to give here is that this collective behavior, we already know that we can only explain it with the rules of quantum mechanics. So there is no doubt that to absorb sunlight, these molecules are fundamentally using quantum mechanics 101 or 100, however you call it, at university. Now, the way we know this is that nature has evolved a variety of light harvesting antenna that actually covers the whole visible spectrum. We have organisms absorbing near the infrared, which is the purple bacteria, the light harvesting 2 complex, which is the yellow molecule that you're passing around and that you will return to me at the end. And we have in the other extreme the cryptophyte algae, which is the green molecule that you are passing around as well. And while they absorb in very different frequencies, they have very different structures, the physical principles that govern that behavior are the same. So one of the main problems that we face here is that In order to understand this system from the theoretical perspective, we really need to be very accurate. It's not enough just to have an insight into how they should absorb. So part of the work that we've been doing, and many other groups around the world, is how to describe as accurate as possible these absorption properties of these molecules. In general, the whole spectroscopy.
You know that feeling of having to rewash dishes that didn't get cleaned? I know.
Platinum Plus is Cascade's best clean ever. With double the Dawn and double the scrubbers, it removes the toughest grease and residue for an irresistible clean and shine. Cascade Platinum Plus. Dare to dish differently.
In my group, currently I have, sorry, I forgot here the name, but this is Charlie Nation, and this is Hallman Oscar Getson. These are two early career researchers working with me. And one of their main aims is that they wanted to be able to predict the absorption properties of these molecules with a very high level of accuracy. And what you can see here, T2 and T3, means two different approaches, two different levels within the same approach. And T3 is the level of more accuracy. So what this is illustrating is as we increase these levels, our accuracy in predicting this is the absorption for this light harvesting complex. The one in purple bacteria, the one that you have in your hands, is becoming better. So we're very happy about this because we now have a theoretical framework and a computational framework that allows us to predict with a pretty good accuracy the absorption properties of systems as large as that molecule. Now you will see, but it's just one molecule. This is not a large system. In reality, this is a system that has 27 chromophores. And if you were to compute the full dynamics in a computer, it will take many days to compute it accurately if you take into account every single atom and every single nuclei. So with the approach that we take, we're able to predict this with an accuracy that I will show you in a second why we need such an accuracy. Now what this represents as well is in that ring that you have, in that LH2 light harvesting antenna, it has two rings, it has two sets of chromophores or pigments. You have one band that is the red band and then one band that is the blue one. The red one here has the chromophores strongly packed. The blue one, the chromophores are far apart. What this is telling us is that individually each band will absorb differently. And this is what we predict in the theory and what it is observed in the experiment. The blue band absorbs around 800 nanometers, but as they become interacting even closer and closer, like in the red band, they absorb at around 850 nanometers. In nature, what happens with this system is that light will be absorbed first by the blue band, so the 800 nanometers, and then it will transfer energy from here to here. So physically, it will be from the blue band to the red band, and if you want to see it in this figure, energy will go from here to here. Now, this figure is also telling us another story, and is that as these pigments interact more strongly, then the frequency that they will absorb will move in that direction. Now, this is very important for one of the problems that we are trying to address from the theory viewpoint, and it's the following. In order to understand the molecular and the physics and the quantum physics behavior of these individual molecules, what we do in the lab, in the molecular system in the cell, they are on the membrane. But doing the experiments on the membrane are not as simple as we would like. So what experimental scientists do is that they work with these molecules. They have solutions of these molecules in which they have used detergents and many other chemicals to make sure that these molecules are isolated from the membrane, and then in a solution they are separated, so you have individual membranes. And this has given great insight into the physics of this molecule. But one of the things that I kept wondering for many years, I've been studying this problem for about 15 years. And just one parenthesis, I remember having a conversation with a colleague many years ago. He had spent about 20 years understanding one particular problem. And I was at the time a grad student. And I told this colleague of mine, don't understand how you can be 20 years stuck with the same problem. At the time, I was a PhD student and I was just thirsty for knowledge, so I just wanted to learn so many things. But now, I fully understand this colleague because I fell in love with the physics and with the understanding of these molecules. I close the parenthesis. So, one of the main problems that have been in my mind, I thought, great, we can isolate these molecules and we can have solutions of hundreds and thousands of these molecules. But these are not how the molecules are in the biological system. Are we changing anything when we isolate them, when we take them outside from the cell? And if we do, if we're changing anything, what exactly is that we're changing? Now, this is not an easy question to answer because it means that we really need to have a very high precision when we measure them in and out the cell membrane. And we need to find conditions that are actually comparable. So if I go and measure in the membrane, it's not the same as measured in the solution because in the membrane, not only that constrained, they're also interacting weakly with other molecules. So the problem wasn't easy, but it was always in my mind, what have we changed when we moved them out of the membrane? And most importantly, going back to the quantum properties, are we changing anything associated to the quantum properties? So this question was in my mind when I had my first PhD student, but we couldn't address the question that was around 2008. But recently, there were some experiments from the group of a colleague in MIT, Gabriela Slaughter. Gabriela and her team had the same bugging question in their mind. So, what is the impact, essentially, of the membrane on these quantum properties of this system? So they designed a system that looks like the biological system. So this is kind of an artificial membrane. It has the same, let me say, material that you will find in a cellular membrane. So this is a lipid bilayer. And Gabriela and her group are able to embed these light harvesting complexes in this artificial membrane, but they are so far apart that they can investigate them as if they were individual molecules embedded in the membrane. So I was very excited when I saw this and I saw the results, because then I said, okay, now we can understand what is the possible effects. Gabriela was predicting that when you take this molecule out of the membrane and when we investigate them on the detergent, on the solution, yes, we get some insight into the quantum properties of these molecules, we get some benchmark of what is happening there, but when we take them out, we make some modifications that actually change in about 30% the energy transfer within the molecule. And 30% doesn't seem just a little thing. 30% is significant change. So I was really, okay, I really have to explain what is happening here. So last year, Chantelle Kulkarni joined my group, and I proposed her, okay, look, this is a problem that I have had in my mind for a very long time. Can we solve it? Can we try to understand this? And she said, oh, yes, let's work on this. And I was very excited because the things that I presented to you are results that we obtained 2 days ago. So you are the first ones to read about it, apart from my collaborators. So this is very exciting because this is the following. So what you see here on the left are the experimental results from Gabriela. The green and the gray curves represent, the green is when they measure the absorption of these molecules on the artificial membrane, and the gray one when they measure it in a solution of isolated proteins in detergent, in water, in a solution that is going to do the experiments. Now, some of you would say, well, they're very similar, like nearly the same, so you only have a little bit of a difference here and a little bit of a difference here. Well, it happens that it is consistent that you will see a shift in the absorptions towards the right, so towards longer wavelengths, from going from the membrane to the disk. From one perspective, you would think that this change, which is just a few nanometers, about 4 nanometers, 5 nanometers in other systems, is very small. You might think, oh, this might be within the error of the experiment. No? So then maybe that's not a real difference. Well, these results are reproducible, which means other labs can go and measure the same, and then we'll come up with the same conclusion. There is a shift in the absorption of these molecules. Now, this shift is very significant because it means that the interactions that are happening within the molecule, so if you have the yellow molecule, there is interactions in that red part, are changing and are changing significantly to affect the absorption. So we join efforts with Chantel, with Hallman, who has developed that very accurate setup to be able to predict this absorption properly. And if you think about it, we need to make sure that we are not predicting something that is changing so that the next approximation will then give me something along these lines. So Hallman has made that possible, Hallman and Charlie and other members in my group. And this is our theoretical comparison. This is to one level of approximation, but we now have the more exact level of approximation. And if you see here, we are predicting a similar shift. In order to do this work, so here the dotted line is the absorption in detergent, and here our black line is the absorption in this membrane disk. This line just represents the light that the blue band in your molecule, the one that you're seeing at the moment, will emit. I'll talk about this later. The most important is that we are able to predict this. You see Chantel is here smiling? Well, that was the smile when we talked a couple of weeks ago when we first saw this. But I'll show you something more. She was even more smiley last week. Why? Because we were able to predict that that small change, what looks small, actually represents that significant change in the energy transfer within the molecule as it was measured for the group of Gabriela in MIT. So she was able to demonstrate by doing these accurate computations that energy transfer from the blue band to the red band was being increased by 30% when it is on the membrane. So it was decreased when we put it on the detergent. And 30%, as I said, might seem nothing, but in terms of the quantum efficiency of transfer within the molecule, it's a significant step. So we were very happy because when we compared the numbers that she was predicting, her numbers, Chantel was in the detergent 625 femtoseconds and on the membrane 140 femtoseconds. Gabriela's numbers are experimentally measured 607 femtoseconds, 875. We were super excited. Now you can say, oh, but you are quite far, 40 femtoseconds here, you are still 35 femtoseconds. Here you are 45, femtoseconds. You are still far. Yes, we're not exactly the numbers. We cannot match the experiment exact, but we can match the qualitative difference that we're seeing there. So this has been really good news for us because now I can then focus on understanding what are the changes in the quantum properties. So while it is been great that from the experimental viewpoint, it is possible to measure all these properties of the molecules isolated, and that has given us and will continue giving us important insight into the understanding of energy transfer and quantum processes there. One thing that I'm starting to understand with this small calculation is the fact that in the biological environment, the quantum properties are actually even more robust. Very, very counterintuitive for what you would expect. Because on the membrane, on the cell, things there are moving all the time. This is a system completely out of thermal equilibrium, but with many different random motions where you would expect that some of these quantum properties might actually be more fragile there. At least that was the thinking. But what we're seeing here is that in the membrane, which produces some pressure, lateral pressure on the light harvesting complexes that you see, you actually see that maintains and enhances that quantum chemical structure of the system. So now, Chantel will continue smiling because we will continue exploring what are the possible quantum effects now when these molecules are analyzed actually in the membrane environment that we have. And what I expect is that probably other quantum effects will be enhanced in that environment.
Downy does more to make clothes because sometimes your work shirt needs to be a soft, cozy pillow. Downy, breathe life into your laundry.
Now, I'd like to move on to something a little bit more controversial. So what I have told you so far, if you were to talk to other scientists from other disciplines, from physical chemistry, other colleagues in California, Greg Engel in the United States, Greg Scholes, Graham Fleming, well, so many people all over the world investigating, we will all agree. We will say yes. So we understand that as far as absorption processes are, quantum mechanics and emission processes, quantum mechanics determines. So we have no problem there. But now we enter into a very difficult terrain here. And it's the terrain in which we are going to investigate whether there are other quantum processes, more dynamical, that actually happen on this molecule. That is where some disagreement still exists, when the issue is not settled. And I'm hoping, or is my aim, that the work we're doing at the moment and the interactions we have with this experimental group in Glasgow will help us advance our understanding in that direction. Now, one thing again that we will agree is that whatever is happening in these molecules is helping us to rethink the way electronic motions and vibrational motions cooperate to transfer energy. So at this very molecular level, you can imagine this as a sea of an electronic cloud.
The government, they are still of Sentinel blood. What you interfere with now is bigger than you can imagine. It is written. It is their time to give penance. If you continue, you will bring down the heavens' wrath. You are but one man. They are no longer your people to save.
Sentinel battery can be used to provide additional power to your ship. Several modules remain unused. Finding more batteries will enable you to utilize the full functions of your command station. There is a Sentinel power core nearby. You can use it to activate the mech and clear a path forward.